The views expressed on Science for the People are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
Welcome to Science for the People. Today we're exploring the edge between the possible and the impossible in the world of complex computing. Welcome to Science for the People. I'm Rochelle Saunders. A little later on, we'll talk to Lance Fortnow, professor and chair of the School of Computer Science at the Georgia Institute of Technology, about his new book, The Golden Ticket, P, NP, and the Search for the Impossible. But first, I'll welcome Scott Aaronson to the show. Scott is an associate professor of electrical engineering and computer science at MIT. His research focuses on the capabilities and limits of quantum computers and on the connections between computational complexity and physics. He is well known for his blog and for founding Complexity Zoo, an online encyclopedia of complexity cases. He's written about quantum computing for Scientific American and the New York Times, has written the book Quantum Computing Since Democritus, and has received awards for excellence in teaching. Welcome to the show, Scott.
Thanks. Great to be here.
So when did people first start thinking about quantum computing?
Well, the idea goes back to the 80s or even earlier when physicists like Richard Feynman and David Deutsch started noticing that if you want to simulate quantum mechanics, so let's say, a chemistry problem, a nuclear physics problem, you want to simulate it on a conventional computer, it seems incredibly inefficient because the basic equations of quantum mechanics have this exponentiality built into them, where like with each new particle you add, the size of the quantum states, the number of numbers that your computer has to store to keep track of what's happening, doubles. So, there might be 4 numbers for 2 particles, and then 8 numbers for 3 particles, 16 numbers for 4 particles, and so forth. And then with 1,000 particles, you would need more numbers than there are atoms in the universe to have a full description. So this, had been sort of understood ever since the founding of quantum mechanics itself in the 1920s. And it had been seen as a practical problem. It's what makes it so tough to solve the equations of quantum mechanics on a classical computer, and why we have to resort to all sorts of approximations and heuristics in practice. So the great insight that Feynman and Deutsch and the others had was that, well, maybe we could turn this around. Maybe we could turn these lemons into lemonade, right? And if quantum mechanics is so hard to simulate with our existing computers, then why don't we build computers that themselves would take advantage of the same exponentiality of the quantum world, that themselves would use the same quantum effects? Supposing that we could build such a computer, call it a quantum computer, we then face the question, what would it be good for? Unfortunately, Feynman and Deutsch were not yet able to suggest, a very good answer to that question. The best that they could suggest was, if you like, sort of the obvious thing. Such a computer would be good for simulating quantum mechanics. Okay, you could have a general purpose programmable computer that you could use to simulate whatever quantum system you wanted. So it would be like, in the old days, every time people wanted to simulate turbulence around an airplane wing, they would have to build a new wind tunnel, right? And today they just have a single machine, a computer that they program to simulate whatever specific system they want. So a quantum computer would be sort of a general purpose quantum simulator. That was the original idea. And to tell you the truth, if we ever get practical quantum computers, I think that will be the most important application of them still. But what really got people excited about this field, what really sort of launched it as a field rather than just sort of like a crazy idea that a few people were thinking about, was that in the 1990s it was discovered that a quantum computer could also do other things. In particular, there are some purely classical problems that a quantum computer could solve much, much faster than we know how to solve them with a classical computer. The most famous example of that is finding the prime factors of enormous numbers. So Peter Shor discovered in 1994 that a quantum computer would also be able to solve this problem much, much faster than we know how to solve it with today's computers. Now, this is important because if you've ever ordered something from Amazon or from eBay or whatever, your web browser protects your credit card number with a code whose security depends on, huge numbers being difficult to factor. This belief in the hardness of factoring is sort of the engine that fuels almost all of modern encryption. And what Shor showed is that if you could build a quantum computer, then that's no longer true. So, naturally that got a lot of people excited about it, and that, really turned it from a speculative idea into a question of, what would it take to actually build this thing?
So what is the actual difference between a quantum computer and a conventional computer?
So a quantum computer, the easiest way to say it is that it's a computer that would exploit quantum mechanics. That, of course, that just punts the question. Now I have to explain, what is quantum mechanics all about, right? And almost any popular article that you read about this subject, takes a sort of lazy way out. And what it says is that a quantum computer is just like a conventional computer, except it's massively parallel. Whereas, a conventional bit is either 0 or 1, a quantum bit, or a qubit, as we call it, is both 0 and 1 at the same time somehow. So, whereas a classical computer has to try each possible answer one by one, a quantum computer can somehow explore all of the answers in parallel. So, well, that would be great, if it were true, but it sort of sounds too good to be true, and it kind of is. So let me try to explain what's really going on here. So, the idea of a quantum computer is sort of exploring all the possible states at the same time, all the possible answers at the same time, has some sort of connection to the truth. But the problem is that, at some point you've got to measure your computer to get an answer out. And what quantum mechanics predicts is that when you make a measurement, you're just going to get a random answer, with some probability that you can calculate. Okay, so then, you might say, if I'm just getting a random outcome when I make a measurement, then saying that the computer is trying all of these possible solutions at once, is just a really fancy way of, a convoluted way of saying, well, it's just trying one of them, and we don't know which one, and we'll find out when we look at the thing. Okay, in which case we sort of jump to the other extreme, which is that this would not be giving us any benefit at all. Here's what most of the popular articles will not tell you, but I will. I'll let you in on the secret. The key point of quantum mechanics, the thing that makes it different from what we're used to in the classical world, is that the way that you calculate the probability of something happening is completely different in quantum mechanics than what we're used to. In ordinary life, we might talk about a 20% or 30% chance of rain tomorrow. We'd never talk about a negative 20% chance of rain, right? That would just be stupid.
That would be weird.
Okay. In quantum mechanics, that by itself doesn't make any sense either. But it turns out that if you want to find what's the chance that something will happen, you have to add up a whole bunch of numbers called amplitudes, sort of one for every way that the thing could happen. And crucially, amplitudes don't have to be positive. They can also be negative. Okay, in fact, they can even be complex numbers, imaginary numbers, like the square root of -1. Okay, the key point is that if something like, let's say, a photon hitting a certain point on a screen, if that could happen one way with a positive amplitude and another way with a negative amplitude, then the two ways that it could have happened can, as we say, interfere destructively and cancel each other out, so that then, in fact, you'll never find the photon there at all. Okay, so this is what's seen, for example, in the famous double slit experiment, right, where you shine light at a screen with two slits in it, and you find that there are these dark fringes where a photon never appears. Now, what's bizarre is that if you close off one of the slits, then the photon can appear at that place. So in other words, decreasing the number of ways for something to happen can actually increase the chance that it will happen in quantum mechanics, okay, because you are then getting rid of the destructive interference. Okay, and this is really the one trick of quantum mechanics that just gets sort of repeated over and over and over again, right? And everything else you've heard about, quantum entanglement and Schrodinger's cat and Heisenberg's uncertainty principle, all just sort of different logical consequences of this one change to the rules of probability themselves. Okay, and in particular, this is true of quantum computers. So a quantum computer, you can think about it as this double slit experiment writ large. So the idea of it is to arrange a gigantic pattern of interference where for each wrong answer, there will be a whole bunch of contributions to its amplitude, but they'll be sort of pointing in random directions. So some will be positive, some will be negative, and on the whole, they'll mostly cancel each other out. Okay, whereas for the right answer, you want all of the amplitudes to be in phase with each other. So all the different paths that your system could take to get to the right answer, you want them to say all have positive amplitude or all have negative amplitude. Now, if you can arrange that, then when you make a measurement of your computer, the right answer will be observed with high probability. And if it's not observed, then you can just run the computer again until it is. Okay, now this is a very subtle effect. As this is, you can see why it wasn't obvious to people in the 80s that this would actually be good for anything. And it took a great series of great discoveries in the 1990s to realize that for a few specific problems, like factoring large numbers, you actually can choreograph this pattern of interference. You can do it despite, not knowing in advance what the prime factors are, which would make it trivial, of course, right? But you can, despite not knowing the prime factors, you can set up a pattern. You can do a physical experiment that will set up a pattern of quantum interference that sort of concentrates all of this amplitude on the correct prime factors. So that was an amazing thing, right? But it's not anything as simple as just trying all of the prime factors in parallel, right? It's really much more subtle than that, and it really took advantage of very special properties of this problem of factoring large numbers, so that already for other sorts of problems like finding the shortest route for a traveling salesman, there, even with a quantum computer, we don't know how to do it efficiently. So, even quantum computers look like, they would have limitations, and it's really only for certain special things that we know how to get this magical speed up.
So that sounds very different than conventional computing. So what does
a
sort of modern day quantum computer, and I'm using air quotes, look like?
So there are a lot of ideas being explored right now about how to actually implement quantum computers, right? What I told you before is the theory. But, just like with classical computers, right, you can be like a virtuoso programmer despite, knowing nothing about what's going on, inside of the CPU case, having no idea of the physics of how a transistor works, right, because it's just a different level of abstraction. Okay, the same thing is true with quantum computers. So, we developed the theory based only on, the laws of quantum physics, which have been sort of, the core of physics for almost 100 years. So we developed the theory, but then there's the question: okay, what actual physical system can you find that will sort of implement this theory? And there are a lot of different proposals, which sort of all realize or all the goal of all of them would be to realize this same theoretical picture. One of the furthest along proposals is called ion traps. So you would take ions, you would suspend them in a trap using a magnetic field, and the spin state of the ion, so whether it's like spinning in one direction or another direction, that would be your 0 or your 1. That would be your qubit. Okay, and what's important is that when you get down to the small enough scale, any physical property at all that can be in either a 0 state or a 1 state can also be in a superposition of those two states. And so what you would need to do, you would need to be able to get sort of any pair of ions that you would like to interact with each other. Okay, so you need to be able to do the quantum version of logic gates, right? In your classical computer, if you go to a small enough scale, what you'll see is basically logic gates like and, or, not, operations that work on only one or two bits at a time. And that, they'll say this bit should be on if and only if these other two bits are both on, something like that. Okay, so a quantum computer would be much the same. You have to build it out of these very, very simple building blocks, quantum operations that just act on one or two of the qubits at a time. Okay, but you have to be able to arrange all that. So with ion traps, you would move the ions around with lasers is the idea, and in order to bring two ions of your choice close to each other and get them to interact with each other just by electromagnetic interaction. And nature dictates to you how the particles will interact, but then using that as your sort of building block, you have to engineer the specific sort of interaction that you want in order to do your computation. So that's one idea. Another idea is what's called superconducting qubits. So these are on a much larger scale. These are actually coils that are sometimes even like big enough that you can see them with a magnifying glass. But they're cooled to close to absolute zero, so that a current through the coil becomes superconducting. Okay, and it turns out that it can then be in a quantum superposition of flowing clockwise and flowing counterclockwise. Okay, and this involves billions of electrons, amazingly. But again, you've now have your qubit. Okay, and then you need to get pairs of these coils to interact with each other. So that's another proposal. A third proposal is to use photons, use the polarization states of photons for your qubits. Photons are great because they sort of preserve their quantum properties, extremely well. Right, so you may have heard that quantum states are very, very fragile. This is sort of what makes it so hard to build a quantum computer. Okay, but photons, some of them have reached us, since the early universe, having maintained their quantum states for billions of years of, traveling through space. Okay, the problem is that, photons, of course, don't like to sit still. They're, they just sort of fly away at the speed of light. And, they also don't really like to talk to each other. So you have to do something to make the photons interact with each other. Anyway, those are, there are also more exotic proposals, but those are three of the most common ones people talk about. I would say that it's not yet clear, which proposal is going to be the best. So, in classical computing, right, there were also lots of different ideas, analog computing, digital computing. Eventually the transistor was invented in the 1940s, and it was just so much better than everything else that it just dominated the industry. And I would say that we don't yet have the quantum computing analog of the transistor. We're still looking for the technology that will really solve all of the problems, right, in building these things. Each of the proposals that I talked about has sort of complementary, strengths and weaknesses, and we don't yet know sort of what's going to be the best way forward. That's why people are sort of exploring all of them in parallel.
This is Science for the People. I'm Rochelle Saunders, and I'm here discussing quantum computing with Scott Aaronson, Associate Professor at MIT. We'll be right back with more Science for the People right after this.
Science for the People is a weekly radio show exploring everyday life from a scientific perspective. To find out where Science for the People airs near you, or to listen to past episodes, check out our website at scienceforthepeople.ca. You'll also find links to connect with us on Facebook, Twitter, and Google+, or to subscribe to the podcast in iTunes. And now, back to the show.
You are tuned in to Science for the People. We've got Scott Aaronson with us today, Associate Professor of Electrical Engineering and Computer Science at MIT, and we're talking about the world of quantum computing, what progress has been made, and how the subject is discussed in mainstream media. So I want to talk a little bit about D-Wave because when you see quantum computing in the news these days, it's all about D-Wave. Can you give us sort of a really quick overview of who they are and what they do?
D-Wave is a company which is based in a suburb of Vancouver, and so they've sort of come to dominate the popular coverage of quantum computing, in recent years, because they claim to already have practical quantum computers, right? And they've sold, two of these things, whatever they are, right? They've sold one of them to Lockheed Martin and the other one to a consortium of Google and NASA. So they have their latest model has 512 qubits roughly, and you can. It's designed just for one specific task, which is called adiabatic optimization. Okay, so even by D-Wave's own account, okay, this is not what's called a universal quantum computer. It's not like a quantum computer that you can program to do whatever you want. In particular, it's not useful at all for factoring large numbers, which was sort of the killer app that got people excited about quantum computing in the first place, or for quantum simulations for that matter. Okay, it's useful for exactly, according to D-Wave's account, for exactly one thing, which is trying to solve these sort of combinatorial optimization problems, right, where you have a whole bunch of constraints, you're trying to satisfy as many of them as possible. So like, let's say, you're an airline, you're trying to schedule your flights, you have all these constraints, right, and you want to get a schedule that does sort of as well as possible. And there is a quantum algorithm that you can attempt to use for those sorts of problems. It's called the adiabatic algorithm. It was first proposed by colleagues of mine at MIT, a group led by Ed Farhi 15 years ago. Now, the difficulty is this. It's that we also know we also know classical algorithms to attack these same problems. In fact, we know classical algorithms that look a lot like this adiabatic algorithm. There's something called simulated annealing. Neither of these algorithms is sort of guaranteed to work, right? That there may be some sets of constraints where they just won't find a solution. Okay, and again, D-Wave, it sort of admits all of this. But both of them may work pretty well in practice. So for the sorts of constraints that you see in real life, right? They may usually give you a solution which is if not perfect, then good enough. Okay, now the key question here and the key bone of contention that has made D-Wave so controversial and that people are arguing about is, it's two things actually. First of all, does this adiabatic approach ever really give you an advantage in real life compared to what you could do with classical approaches? Okay, and it is not at all clear to us that it does. Okay, now on top of that is a second difficulty, that D-Wave's current technology is actually very far from implementing, this pure adiabatic algorithm. Okay, it's instead doing something much, much messier, if you like, and much, much closer to classical computing, which is called quantum annealing. So, you could think of it as being sort of like classical computation, but with a little bit of quantumness thrown in. Okay, and people are arguing about how much quantumness is there, how much quantum effects are there, right? But then on top of that, even if there are quantum effects there, they may not be playing a role in actually helping you solve the problem any faster than you could otherwise. People keep asking me, so is it a quantum computer or isn't it? Right, and people want to have this binary yes or no, way of classifying things, right? And so what I would say is that what D-Wave is doing sort of has the same relationship to quantum computing that would say a dirty bomb would have to a nuclear weapon. Yes, it's really a bomb. Yes, it really explodes. Yes, it really, spreads radioactive waste, over the right. So it really does involve some radioactive effects. Okay, but it's not really what we mean normally in talking about a nuclear weapon, right? And and it seems like it's inherently much more limited in power.
In the media, stories about D-Wave always sound super sci-fi. You hear things like 1,000 times faster and 150 times colder than interstellar space. That all sounds kind of magical.
Yeah, so they've been, you have to hand it to them that they've been, unbelievably effective in sort of getting their story out to the media, and to investors, and to the business world, sort of, without having really made the science case, to the scientific community. And part of it is just that I think just as you were suggesting, right? Journalists like to hear these sound bites. They don't always like to sort of dig into each one, right? So I could take them one by one. This 1,000 times faster. It was actually claimed that the D-Wave machine was 3,600 times faster than a classical computer in some speed test. Now, what was quickly realized after that was that this comparison, first of all, it was by a consultant, who was hired by Google and NASA, who were like, part of D-Wave's consortium, I guess. And what she was asked to do was just to compare the D-Wave machine against an off-the-shelf classical solver called CPlex. And indeed the D-Wave machine was a lot faster. Now, what this was telling you was not that the D-Wave machine was fast, but that CPlex was just completely the wrong software to use on your classical computer. If you use better software on your classical computer, then it will outperform the D-Wave machine. So that was, that was sort of quickly debunked, but not before it had sort of spread out, into the media, and sort of a lot of people had accepted it as fact. The coldest, place in the universe, right? I mean, that there was just a cover story in Time magazine, right? Who the first paragraph was about how the coldest place in the universe, is not in interstellar space. It's in this D-Wave's headquarters in Burnaby. Even if this were true, right? It's not really relevant to how fast is it solving the problem. Okay, but in fact, it's cold. It's so the temperature that they cool it to get it to superconduct is about 20 millikelvin. That is indeed quite cold. It's 20 thousandths of a degree above absolute zero. Okay, but colder temperatures are routinely achieved in many, many other physics experiments. So I've been sort of, not really, not because it's my favorite thing to do, maybe, but each time sort of some claim like this gets, onto the news, onto the blogosphere, people start asking me questions, and because I have this quantum computing blog that a few people read, I feel compelled to respond to it. But it's been very much sort of reactive, very much trying to, set the record straight, after a lot of sort of damage has already been done and a lot of people have already gotten the wrong idea.
I know that for a long time, nobody could kind of get a look inside the D-Wave computer. Is that still true, or have non-D-Wave scientists been able to kind of crack it open?
That's an excellent question. So you're absolutely right that for a long time, we didn't really know what was going on. We were just, trying to infer, and basically, trying to make the point that, well, look, they haven't proved anything, right? And that the burden of proof, should not be on us. It should be on them. But, but this sort of argument doesn't, get you that far with most people. Now just within the last year or two, we have learned a lot more about the devices than we knew before. And the reason is that they sold two of them. The one that Lockheed bought is installed at University of Southern California, and the one that Google bought is installed at NASA Ames Research Center. And so for the first time, independent groups have been doing experiments on these machines, and they've been publishing research papers with the results. So, the most important, I think, was a group involving Matthias Treuer, Daniel Lidar, John Martinez, and some others, where they really tried to do, first of all, to figure out, are there, quantum effects going on in this machine? What kinds of quantum effects? And second of all, to do performance comparison against classical computing. They found that there is some evidence for quantum effects, in the machine. Now, at sort of a local level, at sort of a level of sort of 2 or 3 or 4 qubits, it looks pretty clear that, there's this characteristic quantum effect called entanglement in the machine. At sort of the global level, at sort of all 100 or all 500 of the qubits, we don't really know yet if entanglement is there or not. So the Troyer et al. Group said that they saw what looked like some sort of signature for quantum entanglement and for quantum effects, even at the global level, which by the way would be a prerequisite to getting a quantum speed up. Okay, but they claim to see some sort of signature for this global entanglement. Now, just very recently, there was another paper by Shin et al. Questioning that and saying, well, we have a classical model. We have a model with no global entanglement, but that could make the same predictions. So I would say that that's currently being disputed. Hopefully, we'll learn the truth before too long. But it looks like local entanglement, yes. Global entanglement, maybe. So that's the first thing. But now the second thing is, okay, we can argue about physics, for a long time, but, is it actually getting a speed up, right? Is it actually solving anything faster than a classical computer? And here it looks pretty unequivocal that the answer right now is no, that you can do just as well with your laptop. Let's say, if it's appropriately programmed. And not only is the machine sort of not doing better on any of the sort of problem sets that they tried out, but, the scaling behavior doesn't look better either. Okay, so it doesn't look like, okay, it's just a matter of, they only have 500 qubits, and, once they get to 2,000 qubits or 10,000 qubits, then, the curves will cross, and then it will be better. It's that both of the curves look exponential. It looks like no matter how many qubits you add, that there's not going to be a speed up this way. So in the face of this, a lot of D-Wave supporters have, I think, sort of moved the goalposts a little. And they've said, well, of course, you wouldn't expect to see a speed up today. That's just silly. Of course, a year ago they were saying something different. Okay. But, they say, well, look, the point is just that, we've got, some quantum behavior. We've pried the door a little bit open, and now maybe we can find some problem where this machine does better. Right, or maybe we can improve the hardware, and maybe there will be a path forward to getting a speed up in the future. I can't say that that's impossible, right? The future is a long time, and a lot could happen. But, what it looks like to us is that, it's going to take sort of fundamentally better hardware than they have now, to have a serious chance for a quantum speed up. So, like I was saying before, right, what they're doing, you could see it as like very, very close to classical computing with sort of a little bit of quantumness thrown in. It looks like at the very least you would need to sort of increase the amount of quantumness there, which, in fact is what sort of academic labs all over the world, have been trying to do, for the last few decades. D-Wave's approach has basically been to ignore that, right, to say, let's just take the qubits that we have now, and throw hundreds of them together and see what happens. Right, which, is, in a way it's good for someone to try the experiment, but, it looks like the results of the experiment are now coming in, and they're that, you don't actually get a speed up this way. Right, so it's looking like you're going to need sort of higher quality qubits, and even then, as I also said, we still don't know whether even then you're going to get a speed up using this adiabatic optimization approach. It might be that quantum computers really only give you speed ups for more special types of problems like factoring large numbers.
So just to sort of close things off, if you were going to leave some advice with the quantum computing enthusiast who is also a layperson when they're looking at kind of media reports of what's going on, would you have any advice for them reading that information?
I would say, don't be sort of bowled over just by, claims, it's here and there at the same time. It's, it's more powerful than all the atoms in the universe, right? I mean, people, especially the media, loves to use this hyperbolic language in discussing quantum computing. Now, in fact, it is scientifically fascinating. I mean, it's fascinating enough that sort of I, spend much of my career on it. Okay, but you have to come to it, and furthermore, I don't think, one should go to the other extreme and say that it's all bunk, right? It looks like, the possibility of doing this, is a pretty solid consequence of the laws of quantum mechanics themselves, right? If you doubt that it's possible, then, something is wrong with our current understanding of the laws of physics. And, you could say that would be even much more exciting than quantum computing, right? Much more exciting than to succeed in building a quantum computer would be to fail, because quantum mechanics is wrong. Okay, so it looks like that it should indeed be possible. Eventually. That doesn't mean in 5 years, but it means the laws of physics say that this should be possible. If, let's say, if our civilization lasts long enough, it should give you speed ups for certain special problems, not necessarily for all problems. Okay, but for a few things like factoring, you really can exploit this interference effect to do something quite incredible. But you have to this is an evolving area of science, and you have to sort of look at the claims with the same sort of skepticism that you would apply to anything else. You have to ask questions like, if some group is reporting some experiment, right? What did they actually do? If someone is claiming to get to have a practical quantum computer, well, okay, in what sense is it practical? Does it actually outperform the best that we could do with a classical computer, for example? I think that there are some people who've managed to get very far by just banking on people not asking this sort of question.
Scott, thank you for being here today.
Thank you.
If you want to learn more about Scott Aaronson, you can find him at scottaaronson.com, a link you'll find on our website at scienceforthepeople.ca in our show notes. We'll be back after the break with Lance Fortnow from the School of Computer Science at the Georgia Institute of Technology to talk about his new book, The Golden Ticket, P, NP, and the Search for the Impossible. So don't go away.
On the next episode of Science for the People, we're exploring the science of beauty products and procedures. We'll talk to cosmetic chemist Perry Romanowski, co-founder of thebeautybrains.com, about his book, It's Okay to Have Lead in Your Lipstick. And we'll speak to cosmetic surgeon Dr. Elizabeth Hall Findlay about plastic surgery tourism and safety regulation in the industry. That's next week on Science for the People, on your local radio station, or online at scienceforthepeople.ca.
Welcome back to Science for the People. I'm Rochelle Saunders. I'm here with Lance Fortnow, professor and chair of the School of Computer Science of the College of Computing at the Georgia Institute of Technology. He received his PhD from MIT and held a professorship at Northwestern University and the University of Chicago before joining Georgia Tech. His research focuses on computational complexity, the theoretical study of efficient computation. He's here today to talk about his new book, The Golden Ticket, P, NP, and the Search for the Impossible. Welcome, Lance. Thanks for being here.
Oh, thanks for having me.
Okay, so let's jump right in and also kind of break this down. What is P, what is NP, and why is their relation of interest to us?
P is just simply means the sort of kinds of problems that we can solve quickly on computers. So, for example, if you get into your car and you put into your GPS a certain location and it tries to find the shortest route for you to get from here to there, the number of possible routes that you have is incredibly enormous. Yet the computer is able to use an algorithm to very quickly figure out the absolute fastest route to get from one point to another. So that's that kind of problem. Finding the shortest route in the map is something that we can do very efficiently, and that's something that would be in this class called P. NP are problems where we're looking for a solution. We don't necessarily know whether we can find the solution quickly, but if we actually had it, we'd know it. Loads of examples of problems like this. One well-known one is if I take a map, and you can color any map with 4 colors, so that every neighboring countries have different colors. But what if you want to see if you can color this map with only 3 colors? And if I actually gave you a solution, it'd be easy to check. If I gave you a coloring, you could check that all the neighboring countries have different colors. But the number of possible colorings that you could try is enormous. And NP are the kinds of problems where if we had a solution, we could check the solution. It would be very easy to check that the solution is correct, but it could be hard to find that solution. And so the P equals NP question is simply, is there every problem where we can check a solution? Can we also find it quickly?
Okay, so this is obviously an outstanding question, but what happens if P equals NP?
Right. So if we could make P equals NP, then we could actually find perfect algorithms to do things like language translation, predict the future of things like the weather or finance or just very complicated things. We could come up with very simple algorithms to do. And you could even potentially automate creativity. You could feed the algorithm examples of Beethoven symphonies and come up with a 10th symphony, for example, or finish Schubert's Unfinished Symphony, or create great works of art in whatever style you want, or create visuals that are identical that you would not be able to tell from true reality.
In the book, you take us on a highly speculative journey into a possible future where P equals NP. It's quite an interesting trip. So how much of that kind of idealized future P equals NP world was exaggeration versus what might really be possible?
Well, it's hard to say. Sort of the way that it's hard to predict what the effect of Facebook 10 years ago had on our lives today. And some of it is probably, I wrote this chapter called The Beautiful World, and I tried to come up with a view of what could happen. For example, that we could cure cancer, for example, because we could figure out how to design the right DNA sequences that created the right proteins that would attack an individual's cancer cells, leave all the other cells intact. There might be a few exaggerations. For example, I suggest we could predict the weather a year ahead of time. That might not happen if P equals NP. The weather's just too chaotic to predict. But I think for the most part, most of what I kind of suggest, could actually be very possible. And honestly, I think things would probably change in ways I can't even imagine. Once you're able to sort of do anything you could imagine doing on a computer, which is basically what would happen if P equals NP, the number of possibilities is really just sort of limited by your imagination. There's a dark side to that as well. I think a huge loss in privacy, because you can easily back on information that people are doing based on the actions that they do it with if P equals NP. So you could almost entirely eliminate privacy. It would be hard to do a lot of cryptography if P equals NP, so it's hard to keep secrets. And since you could automate just about anything, the question is, what would people do? So it might cause a lot of problems in the job market, beyond what you already see happening today.
So P versus NP is really, I guess, at its sort of core about effective or efficient computing. So we're talking about there are some things that even our supercomputers of today just can't compute.
That's right. So, we talk a lot about P equals NP. The general belief is that they're different, is that these problems which seem hard to solve really are hard to solve. So the P-NP question really is saying is that there's a limit to what computers can do. There are just some challenges that seem so difficult that, even if you had all the computers working together, just too many possibilities to check to get the best kind of answer. A good example I like to use is Facebook. Is what's the largest clique in Facebook, where a clique is a group of people who are all friends with each other. And it seems like an interesting question to ask. You can't really ask it unless you had access to Facebook's data, but suppose you worked at Facebook and had access to all of Facebook's data. Still, the best way we know to find the largest clique is to try all the possibilities. And the number of possibilities for, say, 100 or 200 size clique is just way beyond the computational power of any machine now or in the future. So it just seems that there are just going to be some problems that, in general, we're just not going to be able to come up with the best solutions for. And so I spent a lot of time in the book just saying, well, how do we tackle these problems anyway? There's lots of, we can do some approximation or heuristics or tricks like that, but the actual always be able to find the right solution just might not be possible.
So this question sort of first came to prominence in the 70s, I believe. So how have advances in computing power over the last 20, 30 years affected this problem, or potentially not really affected this problem?
I think it's affected it in both ways. I like to compare 1971, which was the year that the first paper on P and NP was published by a Canadian, Steve Cook. was also the first year of the first microprocessor that Intel put out. And if you look at the speed of computing from those days to these days, it's an order of millions or billions times faster now than it was back then. So what has that done to the P and NP problem? Well, first of all, it means that for some moderate size NP problems, you can actually search all the possibilities, and computers are just that fast. So if you want to, say, color a map with 50 countries in it, you can just, with a little bit of intelligence, you could probably do that relatively quickly. But what it also has done is it's created a thirst for more. The fact that we have faster computers means we are also creating more data. So the amount of data that we have to deal with now is just tremendous. The amount of data that gets generated from scientific experiments, from social networks, from all sorts of communication. It's just enormous, the amount of data that's out there. And now we're looking for ways to try to understand that data. And so we're asking questions now that even the PNNP is even playing a larger role trying to understand these questions we're asking about enormous amounts of data. And PNNP is kind of telling us what the limitations of the kinds of questions we can ask and try to answer.
These days, we don't just put one supercomputer against a problem. We quite often sort of put a bunch at the same problem in parallel. Does that affect our level of, or the PNP problem?
It does to an extent. You're right. Computers sort of stopped getting faster around 2005 for power reasons. So instead of computers getting faster, what we've had to do is make computers work together, either putting by lots of chips on a single board, and as in multi-core machines, or by having lots of different computers working together in the cloud. And so that's allowed us to sort of keep growing the computational environment and be able to solve larger and larger problems. But it doesn't get us that sort of exponential improvement that you would really need to solve large PNP problems. Those problems still remain hard whether we try to solve them on a single computer or lots of computers working together. There are just even too many possibilities, even if you tie all the computers all working together at all the same time.
You're listening to Science for the People. I'm here with Lance Fortnow, professor and chair of the School of Computer Science at the Georgia Institute of Technology. He's here talking about his book, The Golden Ticket, P, NP, and the Search for the Impossible. So you talk about in your book how parts of this problem were being worked on during the Cold War years, and it was approached a bit differently in the Western world than it was in the Eastern world. Can you give us a little bit of that backstory as to how this problem developed in each area of the world?
It's kind of a neat story because there really was this separation of science in general between the East and the West. And, in these days before the Internet, there was very little communication. And it could take a very long time for results from Russia to reach the U.S. or vice versa. So you see this sort of parallel development in computing in the 60s and the 70s coming out of the U.S. and coming out with Russia. On the U.S. end, it came out of a desire. We were actually building computers, and we were hitting a number of hard problems that we didn't have good algorithms to solve. And in 1971, Professor Steve Cook at the University of Toronto discovered that a certain specific kind of problem, something called Boolean formula satisfiability, seemed to be as hard as any other search problem there was. So Steve published this in a conference, and then about a year later, Richard Karp, professor from Berkeley, University of California, Berkeley, realized that from this one problem you can actually apply it to a whole slew of these other kinds of problems people were trying to solve. Problems like coloring a map, or finding the largest clique, or finding the shortest tour that visits lots of cities. You have a list of cities, you want to find the shortest tour that visits all of them. Those kinds of problems all turn out to be equivalent and all turn out to be as hard as any other problem in NP. Basically, if you could solve those problems efficiently, then you would have P equals NP and vice versa. And that led to an explosion in the U.S. in generating what kind of problems could be NP hard. In Russia, it was a kind of more of a mathematical approach. It came from people trying to understand the nature of computing and information. And in Russia was also, in the U.S., where people work sort of independently. Scientists sort of work on their own. There's no sort of dominating organization. In Russia, things are, at least certainly back then, things were much more centrally coordinated and controlled. And they had a notion called peribor in Russia. Peribor means sort of a hard problem, hard search problem, that sort of thing. So there was the question about, were there problems that were inherently difficult to solve? There was a Russian mathematician who claimed to have settled the problem. So he had some mathematical result that claimed to have settled this issue of peribor. And because of that, he sort of prevented a lot of other research from happening on the topic, kind of slowed down what happened in the Soviet Union, or I think they would have developed this theory much before the U.S. did. But there was this young student named Leonid Levin who was a bit of a rebel of his time and managed to actually sort of discover the same basic concepts that Steve Cook did in the U.S. at about the same time, around 1971, and published his results. But those results didn't make it into the U.S. until several years later. In fact, interesting story, Leonid Levin, because he was a bit of a troublemaker, he didn't get a PhD in Russia. He eventually managed to move to the U.S. He became a grad student for basically a year at MIT, where he just wrote up for a thesis everything he'd done in Russia and was granted a PhD, and then became a professor at Boston University, where he still is today. So it's a kind of a different approach, but yet yielding the same sort of basic question about P and NP, which kind of suggests that it really is a really natural problem if two kind of independent scientific organizations, coming from two different angles, end up with the same sort of question.
Now, there's more than just a lot of prestige to cracking the P versus NP problem, isn't there? I understand there's a bounty on its head.
So the Clay Math Institute, after Fermat's last theorem was this famous problem from the 17th century that was solved by Andrew Wiles in the 1990s, and which gained a bit of notoriety. And so the Clay Math Institute decided it would be great to actually have a list of sort of famous math problems that, if they're solved, will offer a bounty for their reward. So they listed 7 what they call millennium problems, because they published a list around 2000. So they listed sort of 7 major math problems, one of which was, in fact, the P and NP problem. And it's the only one on the list that, first of all, it's the only one on the list that isn't named after a person, which is interesting. But it's also the only one on the list that I think could sort of clearly have practical value if it was solved in a certain way, if we showed that P equals NP. And it sort of raised its stature, not just as, a problem about, what kind of computation can we solve, but actually says that, this is not just an interesting computer science question, it's actually a fundamental mathematical question. And it has driven a lot of very notable mathematicians to really think about this problem, though it still remains, we still don't really have a great idea, and it's really lacking great ideas on how to actually solve the P and NP problem. How do we actually show that either P equals NP or P not equal NP still seems to be very difficult.
Right, because this isn't just a question of proving whether or not P equals NP, but it hasn't been proved that P doesn't equal NP either, which is perhaps even more challenging.
Right. In fact, like I said, most computer scientists tend to believe that they're different, that there is no magic algorithm that solves all these problems. But how do you show that no algorithm exists to solve any of these problems? And there's an infinite number of potential computer programs out there. I need to somehow show that none of them can work. Not just any clever idea now, but no clever idea in the future will actually solve any of these problems. And how to do that is just very difficult. We just don't really have a great approach that would help us sort of eliminate all the possibilities. I mean, if you could show P equals NP, it would be a little bit easier because you just would need to come up with one algorithm that solves some of these problems. But since we kind of don't believe that algorithm exists, showing that no such algorithm exists seems quite challenging.
Always difficult to prove a negative.
Right. It's hard to prove non-existence. I mean, people have done it in other contexts. So, I mean, Fermat's last theorem is was an example of showing that nothing of a certain kind can exist. So it's not like impossible to do, but at the moment we don't have a good approach.
So have any of the other Millennium problems been solved?
Right, so one of them did. The Poincare conjecture was solved a couple of years ago. That's outside my area of expertise. I can't really explain it very well.
No problem. I'm actually just mostly trying to figure out, are these solvable problems?
It's hard to tell. They were on the list because mathematicians have been trying hard to solve them. But every now and then, hard problems get solved.
So what attempts have been made to solve the PNP problem? $1 million is a pretty significant bounty.
Honestly, I don't think the money's the big issue. If you want $1 million today, there are probably a lot of easier ways to get $1 million. It's easier to set up an internet company, for example, or play the lottery. To be honest, in trying to solve the NT. So, but still, I think the prestige factor certainly has driven lots of people to try to solve it. What attempts have been able to try to solve it? Well, people have tried to come up with algorithms. I mean, mostly so far none of them work. A lot of people try to do is say, well, if you have an algorithm that solves an NP kind of problem, it has to work a certain kind of way, and then try to say, then can we show that algorithms that have to perform these kinds of problems are forced to do something that takes a long time? But those approaches usually get stuck because you can't really assume anything about how an algorithm would work. It could work in very strange or mysterious ways, attacking a problem not in a way you would expect to tackle that kind of problem. So those kinds of tricks don't work. You could try to break down an algorithm into its tiny little components. I mean, algorithms are just sort of computer code. Every algorithm can be broken down into a collection of very simple statements, if-thens and copies and setting things equal to each other, just very simple computational steps. In fact, you can break down anything into just basically ands and ors and nots. So very simple operations. And then what you could try to argue is that no single operation can do very much, and so you need a lot of operations to solve these NP problems. And there's been some success if you limit the kinds of operations you can do or limit how many operations you can do in a certain way, but still a long, long way from showing P not equal NP.
So gut instinct. Do you think P equals NP or does P not equal NP?
My gut has always said P not equal NP.
Why?
The world would just be too clean if P equals NP. It would be like removing friction from the world. Friction, costs us a lot because it costs us a lot to do, but if you try to imagine a world without friction, you wouldn't be able to walk, you lose control of lots of things, because everything was kind of
frictionless.
Frictionless, right.
Yeah.
So imagine a world without any computational friction. It just doesn't seem like that's the kind. It seems like we just need complexity. And we need friction. We need hardness to make the world the way it is, to keep it as a complex environment. So to imagine that there's some sort of algorithm out there that sort of makes everything easy, just seems so fantastical that it shouldn't be true. It's certainly not a great scientific reason. I don't really have a great, perfectly scientific reason. Maybe, it's possible there's an algorithm out there that we're just too stupid to find, or it's just a bit more complicated than we're expecting. But the effect such an algorithm would have would just be oddly strange. It's just hard for me to believe it.
Do you think we'll ever really know? Do you think it's a solvable question?
Yes, I believe the problem is solvable, although I'm losing faith that I'm going to see a solution in my lifetime.
So this could be another sort of 300, 400-year open question.
Yeah, it could be 300 or 400 years. It could be one smart grad student coming up with an idea next year. It's just hard to really guess. But my guess is it's probably going to be a long struggle, is that someone will eventually realize that there's a path that'll lead to a solution, and then there'll be a long slog along that path. So people will come up with these kind of partial results, and then finally someone will put it all together. And right now we're at the point where we don't even have that path. Forget trying to actually, make our way along the path. So at least for now, it seems like The solution seems decades away, at least.
Lance, thanks so much for being here.
Oh, thanks for having me.
If you want to know more about Lance Fortnow, the P versus NP problem, or his book, The Golden Ticket, you can visit his website at goldenticket.fortnow.com, and you'll find that link on our website at scienceforthepeople.ca in our show notes. You'll also find links to our social media feeds, to subscribe to the show in iTunes, and to join the discussion by leaving a comment on our episode posts. Thanks for listening, and we'll see you next week on Science for the People.